Now let's talk about the tangent line problem. The tangent line problem was one of 4 major problems that European mathematicians and scientists were struggling with in the 17th century. Also included were the velocity and acceleration problems that you've encountered in physics, Max-Van problems, which are dealt with quite a bit in industry, and the area problems. As you can see, we're going to be covering all of these topics. Now, when you were asked to find a tangent in pre-calculus, you were, I'm sure, asked to find the tangent to a circle. And you may have heard things like touches at only one point, perpendicular to the radius, doesn't cross the curve, that sort of thing. Now, touching at only one point is fine for this curve, but there is no radius for it to be perpendicular to. And this is a tangent of this curve. However, it crosses the line. And this curve right here touches this tangent. The tangent at this point does touch the curve at 2 points. So we need a more rigorous definition. The nice thing about calculus is we are going to start with a secant line. Now, suppose I have a point where x is equal to c, and I have a functional value, that is f of c. If I scooch over here a little bit, and by a little bit, I mean, let's just scooch over delta x. So this will be c plus delta x. Then my function is at f evaluated at c plus delta x. So now, what if I want the secant line between these 2 points? Well, the first thing you always have to find is the slope. Now remember, slope is rise over run, change in y, divided by change in x. So let's see what that is for this curve. Now, I always learned it was y2 minus y1 divided by x2 minus x1. So y2 is f evaluated at c plus delta x minus my functional value here, which is f evaluated at c, divided by, now what is this distance here? It's c plus delta x minus c, which is f evaluated at c plus delta x minus f evaluated at c, divided by delta x. So this is the equation of the secant line. Now, how could we make this a better approximation to the tangent? And the answer is, of course, you start scooching. If this is my point, if I were to start scooching this delta x closer and closer, then as delta x goes to 0, I see I'll have a tangent line. Now, it doesn't matter whether I do it from the left or if I scooch in really close from the right. It should give me the same tangent line if I'm at the same point. Now, the definition of a tangent line with slope m is if f is defined on an open interval containing c, and if the limit as delta x goes to 0 of delta y divided by delta x is equal to m. If that exists, then whatever line passing through CFC with slope m is tangent to the graph. And when I ask you for a tangent line, I'm going to want you to give me y minus this point right here, f of c, all I'm using is a point slope formula, is equal to m, here's my slope, times x minus c. Okay? Now, periodically we get vertical tangents, and vertical tangents are fine in calculus. As a matter of fact, sometimes we look for them. So if you ever take this limit and it becomes unbounded, you get positive or negative infinity, then you know at that point you have a vertical tangent.